Just a couple of things. Next week we are going to Shiba. I went there on Tuesday, and unfortunately the dome is under repair. I wanted to do the balance experiment, and having virtual reality. It broke, they have to fix it, and we will just get a tour, we will see it. The engineer who is working in the virtual environment, Yotam, told me that perhaps he can show us a simulation of the treatment they do for flight anxiety. So there are people coming to get treatment for flight anxiety. He couldn't promise, but he will try to make it work. We found another device. There are many rooms for treatments, and I thought maybe we can get another less fancy virtual reality room, but all of them are occupied for treatment of soldiers. And only the dome was reserved for us, but now it's broken, so we have to do some simpler experiment, and this time we measured real gait, because in Ichilov we did experiments with gait, but we only measured acceleration, right? We measured acceleration, heart rate, respiration, and stuff like this. In Shiba we will really measure gait, walking patterns. Regarding the data, not everybody uploaded yet the data from the experiments. I have given a broad email. So, you did.
יהודה, date modified, ואז אתה יכול לגרור את כל המקום הנכון.
מסמנים פה כמה, אני לא יודע. כן, אבל...
you put me in my hot mobile folder.
Just download.
שזה... כן, לחצתי על דאונלוד פשוט.
Yes. I will put you inside download. Or just to move it in. Okay. Good. Hopefully it works. So I wrote a couple of mails to the people that we need to upload. Once we all the data uploaded, Eitan will convert them in a text file, and I will do some analysis to see what we can do with the data. B'kitzur, we will not talk about this today, and we will do another class, optional, okay, you don't need to come, we will record it on Zoom, where I will say something about the recorded data. I will tell you more about how I imagine this notebook should look like. There are students that do not have participation points yet. They will have optional tasks to put in their notebook to get these points, or we don't have to do anything in addition because you already got your points, but others may want to do it, and that's it.
The participation points, or the 20 points that
yes,
are...
these were the 20 points, but not everybody could get all the points because we were too many students, and and in order not for them to miss out on points, I will put additional tasks in the notebook that are optional to get these points. So this will be some additional analysis, something. Okay. Good. Any questions? Otherwise, today we learn about the EEG synchronization from Yuda, Ori, and Henry. And afterwards, we, Metal and Nitzan, will talk about the gait, posture. The background, give us a background in posture and balance that I wanted to measure in Shiba, but now I cannot because the dome is not good. But it's still very interesting, and they also have nice insights into what you have to pay attention when you do the synchronization analysis for very noisy data, even noisier than your EEG.
Wow.
Okay. Good.
יהודה, runtime?
מה זה?
runtime? tab של runtime.
איפה זה?
Up, left, exactly, down, right. Yes, one. Exactly, press on it, and then you have
runtime.
restart session and run all on the bottom.
אוקיי, כבר הרצתי הכל
בדיוק, מנואלי.
ידנית, אבל בסדר.
Okay, let's go.
Also the MEG, Shai sent me the protocol or the annotation files with the different pictures. You know, there are three kinds of different pictures, but I haven't sorted it yet. So I need to do this also. So I hope once the semester finished, I have time to do this. And so for this optional class, should I just decide on something and then either you come or you don't come, or we want to agree on a date? Maybe first week of semester break, second week, what is
יש שעות מחלקה, יש שעות...
מתי זה?
לא, בטח זה ייקח את הזמן.
I can also ask Rita.
Yes.
זה הדבר היחיד שנוכל לשנות, אחר כך זה התשע.
נראה לי... לא, זה... אולי זה שעות מחלקה משהו. יום ראשון ב10 שעות.
Okay.
אבל לא טוב.
Good, I will ask Rita. I will send you, and whoever can come comes, and the others can look at it on Zoom. And if you have questions, you just write me. Good.
Okay, we can start. Yoda in
No, there's for not to
lock.
okay. Not leave me alone. Okay.
אפשר בעברית או באנגלית לדבר?
שזה מוקלט.
No, I'm a foreigner.
אוקיי.
It's no problem for you, no?
it's okay.
Even Tuli that all the time said, "Oh, I cannot speak in English." You know, she goes to conference and she speaks very well English, and then she's back in Israel. Oh, I cannot speak English. She did very. Tuli, the one that gave the form and explained everything, did a good job, and she goes to all the conference in America, you know, and
So she had 100 papers or something.
yes, and I don't know what was the problem. Okay.
Just before we dive deep, before we all start to talk about all what we wrote down, I just want to do a small reminder about the experiment itself. In the EG experiment, there were two couples. Each couple was left and right, and they are noted by 1 and 2. That means L1 and R1 were the same couple, L2 and R2 were the same couple, and the experiment itself was divided into two parts. The first one was beats. That means that each couple heard the same sound, the same beat, and they had to repeat with the drum according to the beat. And the second part was freestyle, FS. That means that each one of the couple tried to do something in synchronization with one another. During this experiment, we had EEG in our head, all around our head. We had 8 sensors. They all worked, by the way, which is great for us. And afterwards, we got all the data and tried to find some synchronization between in each part of the experiment for each participant. More than that, we had 2 more stuff to do. First of all, we wanted to see some networks in our in the different channels to see which part of the brain talks with which other part. And the second thing is we wanted to do some background noise and to see if what we got is real or it just between the noise. This is what we call the surrogate. To do that, we will shortly discuss about how we done that, but just to let you know, this is a very important part in our analysis.
Which is something that we didn't pay enough attention in our last presentation.
Yeah.
So now it is more.
Okay, you guys can start talking.
Okay, so if you guys remember our last presentation 1 month ago or so, we did a MEG analysis, but it is the same in the sense of the coding. So the first thing to do is to import useful libraries. I don't know if I don't think I need to speak about this again because this is something we already did. Okay, so first we load the data and then we filter. Okay, so we are only interested in this case at frequencies of 8 to 13 Hertz, which is the alpha band. Okay, then we calculate the PLV. I remind you what is PLV. PLV is phase locking value, and it is a parameter that I mean, PLV is a parameter that
it's a measure for synchronization.
For synchronization. Okay, so we get values between 0 and 1, and when the value is 0, so two channels are not synchronized. When the value is 1, so the two channels are fully synchronized.
Yeah, it's my reminder about synchronization. We talk about the phase, not the amplitude. That means that in order to do that, we move to the Hilbert space, and then we take the angle and not the amplitude. And then for each sample, we see if we are in the same phase or not for two different channels. And all what we're talking about is synchronization between two pairs for the entire matrix. That means channel 1 and 2, channel 1 and 3, etc., etc., etc. If we see on the diagonal part, it's supposed to be full synchronization because it's the same channel, and we will see it soon enough. Keep going.
Given two phases, what that we want to see if the difference between each phase remains the same, or apparently just fluctuates a little bit. So this value already checks this one, and this tells us about consistency and synchronization because both are locked in the same variational movement together for the data.
Okay, so in this function, which is something new, we make surrogate data. Okay, so just as Ronnie said in our last presentation, one way to create noise, okay, is just to inverse time. Okay, so if we inverse the time vector, so we just make something that it is kind of nonsense, and this can be used as our noise, which we can subtract from our raw measurement. Okay, this function is computing PLV over time. Okay, which is we will see soon.
This function we've already discussed last time, but what we want to do is we want to, instead of doing PLV for the entire data, we just want to take a small window. This window we want to have about 10 wavelengths. That means that we have sufficient time to see if we have synchronization. And if we're talking about the alpha band, that means that our windows are supposed to be the sample frequency that we have. It's supposed to be 100 Hz if I remember. Then we do it for 8 wavelengths, and we divide it by 8 because this is our frequency. So this is the window, and then we just want to do steps because we want to take this one and to see what to iterate all the stuff inside this window, and just we want to slide it and to get something which is more continuum. This is the step side, and this is just half the size of the window. And it takes quite a lot of time. This is the longest measurement that we do because we're supposed to do PLV for not the entire spectrum, but for each different part.
So,
yeah.
Quick question. So you have a band, right, from 8 to 13.
Yeah.
And you want to have 10 oscillations. So,
yeah.
So it depends now whether you are on the lower end of the spectrum.
Yeah.
Your window will be
it will be wide enough. Yeah, exactly.
Larger, or you are on the higher end?
No, I want the lower end because I want to take the wavelength. Okay. This is why I chose 8.
You take the longest window. So
exactly.
If you would have 13 Hertz signal, you would have more than 10.
Yeah, we have something like
But you want to make sure to have at least 10.
Exactly. This is why we chose the smaller frequency between 8 and 13. If we would take a beta band and something like that, again we will take the smaller one because it has a longer wavelength.
Less windows to make sure that we capture at least
Yes,
the short.
no, it is very important. I now with Shai's supervisor, Professor Gordon, we wrote a review paper about how to do this windowing and putting enough waves into the window, because people don't have this on the radar. They do windowing where they only have 2 to 3 oscillations inside, you know, and
It's sufficient.
yeah, but this is what many people are doing. So, or they put too much inside, you know, that you don't have cannot track the dynamics of the signal because the windows are too big. So, 10 is a good rule of thumb.
Exactly.
Yeah.
I don't know what happens if we take less. I don't know how real the data will be. You know, I mean, if we take just one wavelength, I don't know the response time for the stuff,
No,
because I'm not a neuroscientist, but yeah, I think
No,
the
the point is that your synchronization index will be not reliable when you only calculate the synchronization over 3 or 4 periods, you know. You need to have 10, at least 10, 8 to 10 periods in order to get good statistics. Otherwise, if you just do 3 or 4, it's not significant.
Okay, so after we talked about all of our functions, we want to get to the real data. You guys can keep going.
Okay, so we load the data. Yes, I think you can.
Yeah, okay, we load the
we
data.
just load the data and use the functions, and I think we should
Keep
keep
going.
going to the.
And kept on the frequency that
results.
was given by
Yeah, then
type.
plot
Perhaps the
everything.
100 hertz, I forgot to tell you,
Yeah, it's
not
already.
really needed. One could also downsample this to 10, you know, that it's less noisy, but it's okay. You also need to keep some tasks for them to do in the notebooks afterwards. So this would be one of the tasks to see what is
To
the effect of
subsample.
downsampling.
Okay, so this is just a sanity check to see that all of our channels are actually working and they just moving. This is the first 100 samples of each channel, and this is the amplitude. We see that we don't have anything that is linear or zero. That means that they are all functioning. This is for this is the filtered data for L1 bit. It looks nice.
Everything that you're going to see now, it is multiplied by.
Yeah, it's inside the loop, so everything is for all the participants. You will see all of them, it's quite long. Here you can see the PLV matrix of the real data without any surrogation. This is the surrogation matrix, and this is the deducted one. And we can see again that we have this nice diagonal, and we see some synchronization between different parts. This is for the total PLV, not for this is not the overtime. This is
But the
yeah.
synchronization is always, I mean, the farther you go away, the less synchronization you have.
Yeah,
right?
it looks
It's
like
more
between 2 adjustments
which is-
for all of them, by the way. Not
This is something that you also see.
You should rename the channels because they are not organized by the location. So you
So,
can see
so one cannot say that 1 and 2 is neighboring channels?
1 and 2 are neighboring, but 2 and 3 are not.
okay.
Ah.
That's interesting.
So
Okay.
this would be interesting to know where they are located, you know, because is it more in the back of the head or more frontal, because
I
it's
totally
so
agree with
different
that. Yeah.
functions, right? We have here 2 neuroscientists. It's very, very important whether your frontal activity or occipital, right?
I mean, I think it's the closer the electrodes are, the more probably synchronized they are.
It's not. No, it's not always.
Not
Ah,
always.
it's not just
it's-
moving between all the parts of the brain. That's the
Maybe there are some
I
parts
don't know.
connected which are not.
I don't know.
For
No,
instance,
not in
you
neuroscience.
can see 2 and 3,
Yeah.
the real PLV. It's pretty high. Channel 2, it's about here,
Mm-hmm.
and channel 3 is here.
Ah, wow.
Really?
Yeah.
Okay, so it's not trivial.
Very
It's
much
not
trivial.
Okay, so we need to figure out where this is. Maybe you've got a paper.
Right now I'm working about 2 different papers, so don't have time.
Okay, good.
And this is the theory over time that we discussed.
This is too noisy.
I know, but again, you said that you want for the other participants to
No, I would have taken, you took windows of, I would have taken bigger windows.
Yeah, again, in
Or
our
zoom,
latest
can
talk,
you zoom in maybe? Can you zoom in?
right now, it's quite.
It's not so,
no.
okay, good.
It's not
Maybe we
that
should keep the 50.
But we have the code from last time. We had 2 different ways of smooth that.
Yes.
The first one is by
yeah,
rebinning, and the
yes.
second time is by just using the function of smooth.
Because we don't see here much.
Not here, but wait a second. If we are doing it for the freestyle, yeah, we can see that we have a lot of ones, a lot of PLVs, a lot of very high phase locked. This is the matrix for the
So
freestyle.
wait a second. So this is now for
For the first
one
participant,
couple.
yeah, yeah.
I mean, this is quite pronounced. I mean, even the noisy behavior, can you just scroll up? Here,
Yeah,
and then down.
exactly.
This is really an effect. If this is, I would have expected the opposite. When it's externally driven by the beat, you have more synchronization, and when freestyle you have less, but you find the opposite.
Maybe I'm more this is me, by the way. I'm L1. So
Okay,
maybe I'm
so-
more a free spirit. I don't know. Maybe I don't like the
And
boundaries.
You were
I was.
you
With
did
Metal.
together with
Yeah.
Metal. Okay.
We can check air in a second. Let's go to R1
R1.
freestyle.
Yes, let's see.
But Ronnie, maybe when you're trying to do something, maybe when Ori tried to do like Metal, he was more focused to
lead.
to keep in track because
Okay,
it's more
yes.
it's more
Yeah.
complicated than just listening to something
Yeah, this is
If-
metal.
in
No, it's
lab
R1
conditions.
Scroll down more.
Ah, this is
Not
me.
early.
R2
yeah, my bad.
freestyle is mental.
Yeah, it's my bad. This is metal
Yeah,
in
it's lower.
freestyle. Maybe you kept the lead and I was trying to follow you, so I was more.
I think anyway it
Follow
is
the leader.
You're the
Maybe.
leader.
I think anyway
Can
it
this
is
be
more hard
actually?
to follow
Yeah.
someone
Yeah.
than
Yeah, you have a leader in synchronization. There's a lot of study. A lot of
Okay.
research.
It's nice.
Yeah, so what you said actually,
I mean
Yes.
perhaps because we don't know really what led the beating.
Yeah. Actually, for such a, you all the time record the video also, right?
Yeah,
It's very,
it's very interesting.
So we can see photos of you.
very important.
Video.
No, you didn't record the video.
Yeah.
You recorded for them the videos.
Yeah.
So we can really look if Metal is the leader. Oh.
I think I just tried to follow the entire time.
I thought I'm listening to Ori.
It doesn't look like that, but
We can check this husband and wife and see who is the leader in the house.
Okay. That's a good thing.
Yeah. So again, we've done it for all the participants. We can do 4 hours of talking about each pair, but I think here R2 beats is very synchronized in this part. And R2 freestyle again. Okay, this is nice.
So this is now again the other couple.
the other couple.
The other
Also
couple.
somebody again freestyle. So this is
R2 freestyle. Let's go back to L2 freestyle and see in the beginning what happens. L2 free no.
He's kind of doing whatever he wants, and the other one
Yeah,
is
you
trying to
also
follow
trying
the
to
you also
beginning.
have a leader and the follower.
Yeah.
But only until a certain
Yeah.
certain point, right?
Yeah, maybe he just got,
But I'm surprised that you see this so clearly in the EEG. Did you notice?
I never saw it.
This is the PLV of 2 channels inside someone, not
Yeah.
Yeah.
between 2 different
It's
people.
not between
No.
Two neighbors.
This
So
is
how-
just for you
We will
for
see
yourself.
between the people also.
How do we assessing like leader and non if it's
It's not like someone is more focused, and the other one is more relaxed.
Focus is following the other.
Someone, okay,
We assume that if the PLV is high, he is more focused.
because his inner brain synchrony is higher.
Yes.
I wonder if in the video it's Mita like this.
Yeah, would be interesting to look at. No, but this touches a very important point that also Tuli discussed last week in the lab, that when you're walking around as a young person, you don't think about it. Okay, so if you take the EEG from somebody who's walking around just spontaneously, it has a low level of synchronization. But if you take a Parkinson person or Alzheimer person who has really to focus on the walking, you see much higher synchronization.
But then we should see the same results for both freestyle and beat if you are trying to focus, right? If the
Right, because
He needs to focus on any.
and no, we see different
The
results
level
for
of
the
focus
beats
is different between the two conditions. When you do a beat, you have the beat and you have the drumming of the other participants.
Yeah.
It's harder.
And here we see less PLV for the beats.
yes.
For all of the participants. Less PLV.
Yeah, because maybe you have more input.
Yeah, this is freestyle. This is the L1 freestyle that we just talked about, and this is the beat.
Yeah, but if you have more input, you know, then maybe this disturbs again. And if you just focus on one thing, then you have a higher level of synchronization. Because if you're, as Shai said, you have the beat, the external beat, and your partner,
Yeah.
then you
Many tests makes you lose like
yes,
focus on
yes,
one.
Yeah.
yes. Then
Maybe it's more predictable the beat than working with a partner.
and I think we saw this also in Parkinson people when they just
I got Parkinson.
no, when they just walk, you didn't walk, you were sitting and drumming, so it's completely different. But when they were just walking, they had higher synchronization than when they had to do something in addition, you know, when they had to turn around, for example, you know, or go to a narrow passage. Then they had to focus on two different things, and somehow this disturbed synchronization. I think there's something into the explanation. Yeah, okay, good.
It's really like that. Okay, so this is just the first part of just looking at the
And we
building.
see the surrogates is always very,
Yeah, it's very
so
low.
it's really significantly different. Okay, very nice.
But again, it's nice to see that for all of them. That means that what we get for all of the participants is real. And I
But
like
you
it.
have different, when you look at the matrices, they don't do, I mean, you have always this red on the diagonal, but also in the here, the upper triangle is not so much pronounced, but when you go to the previous one, you have more, you see this? You have
More
so
red.
this is more red in the
You see, move away from the
no,
diagonal.
when you move away to the upper corner of the triangle.
Yeah.
Like this.
Yes,
Yeah.
yes, exactly. So this is very individual.
Mm-hmm.
It is symmetric.
Yeah. The matrix is symmetric. It's channel 1 and 2 or 2 and 1. So yeah, it's the same.
Okay.
And actually, we can see what you just said in the next part, which we talk about networks.
Can you please can you repeat what you explained about the metrics? I don't see the differences.
So look at this, for example. Most activity is going on the diagonal, right?
I'm a little bit colored blinded.
Okay,
I
that's
can see nothing.
No, this difficult thing.
Yeah, what?
So you have in the diagonal, I mean, in the next to diagonal,
Ronnie talked about, okay, so we're in the diagonal, it is all red because it's each
one
channel
with
which
each other,
is
so
with itself.
synchronization is wrong.
And around the diagonal it looks like it is more synchronized.
Okay.
But Ronnie talked about this part and this part,
Which are the same.
which are the same.
Compare.
We can see there is also some synchronization there, and it is changes between the with the people and the tests.
Actually, it doesn't look like it very changes.
No, but as you scroll down to between like 1 and 2,
Here it's less.
But here is much less. Yeah.
Here it's less, but for the
but here is still 2, L2. So maybe when we move between people,
So basically, the most is going on the off diagonals.
Do what?
The off diagonals,
okay.
not on the diagonals, but
Okay.
off. But we don't have the information about what a channel is located where. So this would be also interesting to see. Maybe when we plot the networks. For this, the networks are good to see what connection is the strongest. On the plane. Okay.
So
and this leads to
this leads to the networks.
Next
Exactly.
thing is networks. Okay, so here we just create the functions in which we make our networks. Okay, we create. You want to talk about the threshold now?
Yeah, the most important thing that we don't have a real number for is the threshold. The threshold is
okay. So in order to determine which nodes are connected, we need to define a threshold. Okay, so if the PLV is higher, any value we define, so the nodes are connected. So this is kind of a free parameter you can choose and play with. Okay, so we just define the threshold to be 0.5. I remind you, PLV is between 0 and 1. Okay, so in this case, if the threshold is above 0.5, 2 nodes are connected.
I think a better idea is to choose a threshold of the surrogate data.
it's very low. It's very low. It's something like 0.1.
Yes,
And they are all connected if we choose that.
I would also suggest, but you can do this only if you have enough data. If you just have this few data, then
We tried very low
it will be-
threshold.
it will be,
They're all just connected with
will be all
one big.
connected. But you're right. This is usually what people are doing. They take, but they take then 100 surrogate pairs,
Yeah.
you know, and this way they decide on threshold, and
so since we only have one couple,
you cannot do it.
Yeah, again, you can see that matrix is very, very low, like 0.2, and that means that almost.
So 0.5 is kind
Yeah, but again, we can just change it within just one click, and we were going to do it live.
Ooh.
Yeah,
Wow.
but
Right,
in a few moments. Yeah, so when we choose the threshold for be 0.5, and we look on all the participants. Yuda, do you want to talk about what we've seen before?
Yes, so this is L1 bit, this is Ori. Okay, so you can see these are the channels. Okay, channel 1, channel 2, 3, 4. Okay, and you can see which of them are connected to each other.
What is the node size?
Well, I don't remember by heart.
I think it's 50. It's written a little bit down.
Yeah, but it's different.
Yeah, what is
What
why
does
it's
it-
different
What
between
does it tell
channels?
us about it? Maybe the number of connections.
I think so. I think that the bigger it is, the more connections.
4 has
Six are the
3
same
and
size.
6. Yeah, It's the
Yeah,
number
we
of
can look at
connections.
this next one. It's the same thing
Yes.
when they are
okay.
connected. Yeah, exactly.
But wait a second.
In channel 6, we don't see it because it doesn't have any connections in this part.
So, can you show again the other? Good.
Yeah.
So here we have this. So channel 4 and 6. We don't know if you know which.
Yeah,
which
yeah.
one? This-
It's 4, 5, 6.
It's in the middle.
Nice.
4, 5, 6 is in the middle.
And 2 and 3 is one here and one
1, 2, and 7, 8. 3 it's
Ah.
on the back.
What I wanted to show, which is quite interesting, is these guys, which are just. We don't have a node, a big node. They're just connected by one with another, like that.
And this is again you.
No, this is for L2 freestyle.
This is
And
the next one.
and we see the same thing for R1 freestyle. And no, sorry. For R2 bit again, but it's not the same. What
This
they
is
want.
everything like that.
I'm R1.
Wait a second, it doesn't. Remember?
Well, so we have a zoo of
Yeah,
networks here.
but if we put them side by side, I guess it becomes the threshold.
Maybe.
Yeah, okay, so let's change a second to threshold. Let's do it by 0.8. Let's see if anything connects with I threshold. 1 second. Sorry, not here. Also. No, because I need to change that. Where's the threshold? Threshold here. Sorry, 0.8 because that's the input. And when we do that,
Almost no.
now you
Thing
can
is
see they
connected.
are none of them is connected, which is great. This is what we wanted to see. Although here we've got two which are connected. This is a very, very strong link of channel 2 and 3. Do you know?
I can't explain it. 2 it's here, 3 it's here. 3 is always noisy, very noisy, because of the muscles here.
Yeah, and for the rest, we don't see a thing. Only for one participant, we see something.
the back of your head.
Yeah. But why this channel is related to...
It looks like this is the strongest link because for the rest, we don't see that.
Very long distance.
But only for.
Yeah, but 0.8 is too complex. We see in the matrices also that it's hardly,
No. But again, we get this link, which is quite unusual, just this one. If we take it for something lower, like 0.
Like 0.2 or something.
Let's say. So we
but you didn't see any pattern emerging, right?
Actually, we did not. We tried to compare between the participants to see how L2 freestyle and R2 freestyle are with one another, and we did not see any sync between the participants. No.
Expected usually because
I'm very connected to Metal, but
Yeah.
apparently not so much.
effects are very small, and then you do these networks usually by averaging over many people.
So no, we did not see anything unusual.
Okay.
We tried different, but no, they all look very different. But again, the code is working, so I don't mind that. So lastly,
It's
what we wanted to do is to see if there is any synchronization between the different partners. That means L1 and R1 and L2 and R2 in the freestyle. And here for the surrogate, we just chose the different participants from the different pair.
yeah.
And when we do that,
And you do again all channels
all channels,
to all channels of the other one or the corresponding channels?
corresponding channels. No, it was just two when we tried to do 1 of 2 and 1 of 3 and 1. We just do channel 1 with channel 1, channel 2 with channel 2 of the different
Yeah,
participants.
that's
So this is the P over time. If you can zoom in and see when they look quite the same, but only for L1, R1, channel 3, they look quite the same in some of the time. And when we look about L1, R1 bits, we barely see any synchronization, only in channel 1 and channel 8. I don't know, but again, look at the value.
oh, good. Yes.
Look at the value. Super, super low. That means that we don't have anything.
You don't have a good link.
No, apparently not. And it's for all the participants. You see, this is 0.04, 0.07 is the maximum, 0.04, 0.05, nothing. We are not related at all the couples. That means that we did not get a real synchronization between, for the total PLV.
Normally these are the values. Maximum it's 0.1.
Really?
Yeah.
Ah, okay, so we are in good shape, mate. I didn't know that.
Actually, you're right there. I had some study on range of causality, and we were also in this range of 0.05 and 0.08 maybe maximum. So,
But what we can see is that we got more synchronization in the freestyle. This is the bit. You see, these two are blanked, all of these. But in the freestyle, we've got something for all of them, and it's the same for the other couple.
Yeah, but you need to compare to the surrogate and.
This is real minus surrogate. It's already in the
yeah,
code.
Real minus surrogate.
Real minus surrogate for all of them.
Uh-huh.
You see?
Yeah, right.
That one, link.
And here again. Real minus surrogate. Which is nice.
Should it be real minus surrogate or should it be real divided by surrogate? To see how much
We want to subtract.
Why should you
subtract the
divide by
noise.
the noise?
We want to subtract
See
it. We
how
want to
much
see if
you
we
are
are
above.
above it. How much we are above? We wanted to have an absolute value between 0 and 1. No.
If you
You tell
divide,
me.
you have the percentage you are above. When you do it like this, you have different effects.
I don't know, maybe.
I think one
Again.
can do it.
The difference is like a shift. I think it's only a shift.
It's a shift, yeah, how much you shift it.
Because let's say how much is like background noise, just
I just wanted to see
Yeah,
if we are
we do it
above or
later.
below it, to see if we have synchronization.
Okay. Yes. Yeah, it's not so easy. I mean, that's why there are people that write their PhD on this, you know. You would have solved it on one afternoon, and where is Shai working on this?
Yeah, by the way, we can see that they are,
Years.
this is the real PLV. We can see that these two disappear. That means that they are not real. This is the real minus surrogate. So I think this is nice way to see. The surrogate data is significant.
I mean, that all the, maybe it's also not good to show also the upper and lower triangle because it didn't calculate this. You just calculated the diagonal, right?
Yeah. Yeah. This is just the diagonal.
Because the massive blue from the upper and lower gives the impression there's not much going on, but there is a little bit going on, you know. And
Again, we are not data scientists, we are not brain scientists, so we don't neuroscientists. Don't really
yeah,
know how
but
to comprehend with that.
it's not so bad.
If you say that 0.1 is the maximum, so
Yeah,
it's quite maybe another.
it's very big effect, you know. It's you cannot compare it with in one person synchronization with the coupling to another one. It's by an order of magnitude below.
Maybe another thing to do, especially when the PLV values are low. Maybe I don't know if people do it. Maybe normalize the data by some Magdalene surname. For example, I don't know the power of the sensors or something like that.
Yes.
not to allow the amplitude as well. So the
I mean,
difference.
if one sensor is greater in power, then you get more.
But again, we are talking about, we are not talking about amplitude, we are talking about the phases.
Phase, so
But maybe the noise affects the phase, I don't know.
yeah.
I don't know actually how these sensors are working, but yeah, in our lab we are doing it all the time. We're constantly normalizing the data that we get from our sensors because we are using sensors that are, let's say, have efficiency of 40%, so we don't know if what we got is noise or it's real. So
It's an astrophysics.
no, a molecular dynamic physicist.
Okay.
Yeah.
It's
But
not
we are
also
u-
doing astrophysics.
No, we are in Yoni Tokyo's group.
Okay. I
Yeah,
see.
we are studying ions and stuff like that.
Yeah, but also many times you measure the relative amplitude.
So again, just to stress it, what we saw at the beginning with the high levels of synchronization, this was a physiological effect within the same organism. Okay, what we see here is a psychological effect. Okay, because the two are not Siam twins. You're not connected physiologically. You're connected psychologically when you do the same experiment. So it is expected that the effect is much weaker, and it's about an order of magnitude. Huh? Good. I mean, what do we expect from two experiments? You know, usually you have to run the data I worked with Granit on, they did 400 couples over a couple of years, you know, and then you get some effects, but for two couples.
We don't have enough statistics.
Yeah, it's good to practice the methods we learned, but we cannot derive much from the results. Okay, very good. Yeah, thank you. Good. So
Now? Now?
yes, we want your
Ronnie, one of the main things that we started working on when analyzing light curves is really to determine how do we pin
yes.
the width between each time beat.
Yes. Yeah, that's critical. Yeah, I can imagine. So you take from which observatory? You take from the
Chandra main Chandra X. NASA X.
Ah, okay. Where do they measure it? Where's the?
Sorry?
From where is it measured? In Hawaii or where?
No, it's in outer space.
Ah, it's
It's a satellite.
together with
Satellite.
the James Hub.
No, James Webb is the infrared.
טוב, אז הייתי אחראית
And
על
it was launched
הסיסטם.
like recently, and
Yes.
Chandra was launched in 1999.
Ah,
וואו, לא רק.
and this does
In X-ray.
high energy.
High-
Okay, X-ray. Bursts. Okay. Good.
Okay, now we welcome L2, L1,
R1. And the photographer also. Yes. So we're going to talk about the human posture and the face synchronization we'll talk about at later. And right now we had two papers that we worked on. This paper is random walking during quiet standing. So basically during quiet standing the human body keeps moving in an erratic and possibly chaotic fashion. So, posture sway is very indistinguishable from correlated noise, and it can be modeled as a system of bounded and correlated random walks. That's what they did on their paper. I didn't write the name. It's J.J. Collins and C.J. De Luca, I think. Human.
What a catchy title, no? I mean, this is. I like the paper is nice. I read it as a student. It's already old paper from the beginning of the 90s or end of the 80s.
Something like that. I don't remember the exact.
He wrote this when he was a PhD student, I think, and it became so successful. I mean, he did also other good things, but he got quite easily a professorship. Yeah.
A human postural control system is a physiological system that can be described as a noise-like fluctuation, where the output is highly irregular. It's basically a physiological chaos, where a chaotic system is usually characterized by the existence of an attractor that has some fractal structure and has also a sensitive dependence on initial conditions. And we also learned in the beginning of the class about the correlation dimension, D2, where the chaotic system is characterized by, and we can do it by some experimental time series, where we calculating the correlation sum, which is the fraction of pairs of points that are separated by distance less than epsilon. It's a very tiny value, so it doesn't really it is significant, but not that much. As you can see in the equation, we have the Heaviside function that depends on the points of the time series. And after we calculate the correlation sum, we can do a log-log scale of this correlation sum in order to calculate the correlation dimension that can says how much the system is complex in its chaotic sense, and we're supposed to get some linear slope that it is very nice if the system is chaotic.
So this correlation dimension looks very much like what we call it for the fractal dimension, right? But it's another way to characterize the, fractal dimension we looked at to characterize structures, right, in space. And then we went to look at time series, and we said, oh, the same idea with the roughness. Remember, we had these coastlines, and the rougher the coastline, the higher was the fractal dimension. Then we took the same idea to time series. Time series also have this roughness, and how can we characterize the roughness of the time series? And we said by the Hurst exponent. So this is one way to characterize the roughness. Another way is to take this correlation dimension. It's a little bit a different approach, but does similar thing.
Which one is easier?
The Hurst exponent. It's straightforward. It's just DFA, and nothing you can do wrong.
Yeah, this is calculations.
Yes, this is a little bit more tricky, but they quantify also slightly different things.
So the next thing they talked about is the linear of exponents. We also talked about it at the beginning of the class. And it is basically how the system sensitivity is to initial conditions. And this exponent quantifies it. As you can see, we also talked about this in the beginning of the class, if you remember.
Yeah, so x of t is the time series, and then you look at the trajectory, how the system develops under different initial conditions, and when it is basically the difference between two trajectories calculated for slightly different initial conditions, when the difference between them diverges, you have a chaotic system, right? This is what your quantum exponent.
It's local instability. I don't know if
Plus
it's
minus.
chaotic. Okay. Well, we would say that it's local instability, which may lead to chaotic behavior.
Right.
Not exactly.
In the paper they said that if it is a positive exponent, then it means that it can be a chaotic system.
Yes. Yeah, because you see it there, when you have the lambda, if it is positive, it diverges, right? If it's negative, it converges. If it is zero, then you have some kind that is more stable. You get maybe some limit circle or stuff like this. Okay.
So if we're having a time series which is very short or noisy, there may be some results of false positive linear of the exponent. So it can look like it's a chaos system when it's not actually is. So as these guys did before, it's the surrogate data technique in order to detect if it is a chaos positive, if it's false chaos positive or not. And I don't know if I need to say the idea again, to randomizing some property of the original time series, and then the surrogate dataset needs to be processed as the same algorithm as the original data. And if we are getting the same results, we can see that it is important. So what they did on the paper is they checked if posture sway can be modeled as a correlated noise process. So they quantified posture sway by measuring the time varying displacement of the COP, which is the center of pressure, of each individual foot. And so you can see we have the original data and the surrogate, and it's basically the same.
Wait a second. So you plot there.
They plotted.
Yeah, right. So this is from the paper. So
yes.
Y of t. So what you see there is not.
It's t and delta t. Tau is just an
but it's not x and y. So center of pressure has two coordinates, right? And this direction is the x, and this is y. But here you see only the y coordinate, so it's, I don't know if it's
And how shifted you
I
are
think
from
they
the y?
worked straight.
exactly how you no, it's not shifted, it's a
How
time delay.
pressure you put on a certain direct in the y direction?
Yes, so it's you're swinging in this direction, for example, but here they plotted with a time delay, so they plot on the x-axis at time t, and on the y-axis at time t plus tau, right?
Your next step, that means? Like,
No, it's not. There's no step. It's just.
No, it's human postural.
it's your
How-
next
Just like
move
that.
to...
It's
It's
basically
just the
in the
control
future.
system.
You know how it looks like.
Yeah, okay.
And what happens if you have a completely deterministic,
Just straight line.
cyclic behavior? What would you get? I mean, if it is, for example, a circle. A sine. Okay, if it would be a sine, what would you get? A circle. Right? But you don't get a circle here, you get some many circles on top, so more interesting pattern.
Why they don't do just concurrent sections? This is the way to identify the chaotic behavior. Why not
You
take
can,
the data
from
and
here
to
you
make...
can, this is kind of a concurrent.
Yeah, kind of, but it's not exactly, it's not really. Maybe they
Yeah.
are leading afterwards to that.
They just wanted to check the correlation of the noise process, not
Yeah.
the chaotic.
But here they compare now to surrogate, and
Yes.
they say it's very similar. Or what did they say?
Yes.
Or what? Yeah, okay. No, it's
Just
not
the
similar.
fluctuations, not, but it's all progress the
The
same.
same trend?
Oh, no, okay.
Mm-hmm.
This is what all the time is.
Okay.
Yeah, but what I wanted to say also, so they do here a surrogate, which is phase randomization. You remember what was the phase randomization? How you do this? There's also another way to do surrogate. One is a couple different pairs. One is time inverse, and Fourier phase randomization is you do a Fourier transform.
Yeah.
You get an amplitude, right? The Fourier transform
Yes.
is a amplitude spectrum and a phase spectrum, right? And now you keep the amplitude spectrum, but you mix the phases.
And how do you mix just randomly?
You randomly, you have actually you have these Fourier coefficients, right? And each Fourier coefficient is a complex number that has one part amplitude, one part phase, right? And then you just take from the one Fourier coefficient, you take the phase and put it to the other Fourier coefficient, and vice versa. This way you mix it up. So you keep the amplitude, but you mix the phases. This is one way of doing surrogates. You basically destroy any memory in the data, in the phases, right, of the signal. And then you do inverse, and then you have still the same frequencies, but at different times, basically. You know, different order. Okay, good. Then.
So from these results, what we said before, if it was a chaotic system, if it was a chaotic system, there's supposed to be a linear curve, and we didn't get that in any of the surrogate data or the data at all. And which means that it actually behaves as a stochastic system, which is more random and not that sensitive to initial conditions. And also the linear power exponent, you can't really attract anything because, as you can see, it's not linear. We can't get out the lambda. So what they come to a conclusion that the posture sway can be modeled as a correlated random walk and not noise.
Because a random walk is not chaotic, it's stochastic, right?
Yes. In correlated random walk, the system has memory. So each increment is correlated with the past increment and future increment. And this correlation can be quantified with the age exponent, as you can see in here, from the average of delta y square.
This is not the first experiment.
Yes. And tau again is just interval of the time. A scaling exponent can be in a classic way from 0 to 1. The most normal random walk is 0.5. They did this technique of the random walking on the original data, and they got a short term and long term, which is when age is above 0.5, we have the short term, which means it's a positively correlated random walk, and the long term it's negative random walk. For age equals 0, what?
Yeah, you get a crossover, right? You will have.
Yes, on tau equals 1 second. After 1 second, they got a polarity.
Yes.
So it changes. It's a positive or negative after 1 second.
So you have for the on the smaller scales, you have it positively correlated because the age exponent is above.
Yeah, it's really
0.5.
fast. It happens really fast, and after a very long time, you can see that.
It's anti-correlated.
You can see because it's down here.
Yes, very good. You see it there. Yeah.
Basically, but after a very long time, age goes to 0. Yes.
Okay. So this paper was done before they developed DFA. So they calculated the host exponent a little bit more complicated way. Now it's much easier to calculate the host exponent.
Yes, what they did after they got the results in here is they also did a shuffle surrogate of the data, and they got the classic random walk of 0.5. So they said that the COP data suggests that the posture control combines open loop mechanism in the short term and closed loop feedback in the long term. And now before we're gonna start speaking about the article,
so just maybe about this crossover. So when you remember we talked about what makes a positive correlation and what makes an anti-correlation. You remember this? We had this example of temperature data. Temperature data are positively correlated. Why? Because you have areas of low pressure or high pressure and they move very slowly. So the temperature of today is correlated with the temperature of tomorrow. If it is warm today, it's more likely that it's also warm tomorrow and vice versa. So this is basically what you see here at the beginning until 1 second. This means that you have a tendency of the postural system to move in the same direction.
Like
Okay?
inertia. Like inertia of the process.
It's like an inertia. However, if you would continue doing this, you would fall over, right?
Yeah.
So that's why you have to act against it on a time scale of 1 second, because if it would be 10 seconds, you would definitely fall on your nose, right, or backwards. So it's on a time scale of 1 second, you have to move against this, right? So it's anti-correlated.
So anti-correlation is like self-balancing to go
Yes,
to stability?
yes.
Okay.
So the anti-correlation, we had this example of when you have a control mechanism of a thermostat, for example, and you want to put the temperature of the room exactly at 25 degrees, for example. Then you measure the temperature and you get a little bit above. Room is not a good example. It's more a physics experiment in the lab where you have to keep exactly a temperature of, I don't know, 3 Kelvin, okay? And you do it by heating and cooling. So you're a little bit above, you need to cool down, okay? You're a little bit too low, you have to heat up. So, and this is anti-correlated.
Negative feedback.
Negative feedback, and this is negative feedback, otherwise you cannot balance yourself. It's very nice. It's,
the robots, the very advanced robots that walking also follow the
Yes.
same technique?
Yes.
Oh really?
Yeah, they need to know all of this, and it's walking, but also I talked once with an engineer who's doing robotics in Boston, and he told me you have no idea how difficult it is for a robot to pick up, I mean not now not anymore, but 10 years ago, to pick up a raw egg. Because you have to, first of all, you have to coordinate the hand movement that you hit the egg, but not, you don't hit the egg, but you grab it, and then you should not grab it too strongly, but also not too loosely, you know, because in both cases you would either it fall down or it would smash. So things we don't think about, and it's very natural for us. When you construct a robot, you need to know all of this, right?
How to pick an egg.
How to pick an egg.
How to pick an egg.
And when you look at hand movements, they're also correlated. It's correlated movement. Okay? And I don't know if I said this already, if you lose this correlated movement, if somebody loses this correlated movement because of neurodegenerative disease like Alzheimer, they are not able anymore to open a door or to eat properly because they cannot coordinate it. You know, they don't have this positive and negative feedbacks. Yeah. Okay, good.
נראה לי נחליף מקום. כן, עדיף. Okay. So now we will talk about phase synchronization. What we have in phase synchronization, we have two oscillating systems that they move in a way that their cycles match up or become more in synchronization with each other. Postural sway can be seen as a coordination of these oscillations between different parts of the body, the upper part or the lower body. In healthy person, you want to see a small synchronization between the parts. So if you get analysis that you don't have synchronization, it is good. You are healthy. We can see on this graph from one of the lectures. On this graph, you have the x-axis is the time and the y is the phase. So the blue one that is going up, you have you don't have synchronization. The red one that is more looks like a plateau, you have a synchronization, very good synchronization. And the graph that is going down, you see a weak synchronization. We can see it on these graphs that the x-axis is the phase or angle, and the y-axis is the probability to that. So when you don't have synchronization, the probability is equal to all the phases. And when you have a strong synchronization, you have a very sharp distribution at some phase. And when you have a weak synchronization, you also have some peak of probability, but he is more larger.
So this is actually phase difference. So you already take both oscillators, you calculate the phase difference. If it is, if you have these plateaus, it means no difference in the phases. And you get a sharp distribution, a sharp histogram. And yeah, and if you have everything all over the map, then you get phase differences that are, when you do a histogram, you get a flat histogram. Yeah.
So the second article that we saw is his name is phase synchronization in regular and chaotic systems. So the main goal of this article is to show that there is a phase synchronization at both in periodic and chaotic systems, like in theory and in practical. They also wanted to show that phase synchronization can reveal They want to show that phase synchronization can show a synchronization in weak interactions that other traditional methods can't show this because they are focusing on amplitudes, and this method is focusing on phase. In this article, they apply a phase synchronization method to analyze the body sway data from people. There were two groups of participants, healthy and sick people. People were asked to stand quietly on a force plate, like you can see on this picture. You have the force plate. COP is center of pressure on this plate. So the output of the measures is the coordinates of X and Y of center of pressure under the feet of the standing subject.
But the subjects were not walking, they were just standing. So
Yes, like this, quietly.
Quietly, and two conditions, right? Eyes open and eyes closed.
Yes, I will
I
elaborate.
will talk about it.
Yes. So in addition, the experiment measured people in 3 different situations when their eyes was open, closed, and also they showed them some video. So in health, the results was that in healthy subject, the movements in left and right and back forward were independent. No synchronization, and in sick subjects was a synchronization, but when their eyes was open, they saw synchronization that is not at the beginning, after some time, but when the eyes was closed, they see synchronization immediately from the beginning.
This reminds me of an experiment, sorry to interrupt. I did this also once, and this experiment was, I didn't know what they are measuring at this time, but they had also a force sensitive platform, and then they showed pictures. And sometimes the pictures were neutral, sometimes they were about tasty food, and sometimes about scary images. Yes, and this was when I was a student, and then you really could show that when there is something nice, you are more gravitating towards the screen, and when it's scary, you go backwards. Without the instruction is to stand as still as possible, but you still do it unconsciously, that you go away from something scary. It was
You go towards the food.
and you go towards the food, yeah. Also, you really don't want it, you know.
Why were in sick subjects there were more synchronization?
In what?
More synchronization in sick subjects. Why is that? Do you know?
I think it's
Biology?
like Ronnie said before about.
They have
For example,
dependence on each other, because it means like if you, I don't know how to say it's a layer,
yeah.
then one leg is depends on the other. So if you're sick, you have some problem, you need to control to help one another.
You're more
Actually,
You need to
this
be
is
more
what I
focused.
thought also, but then a couple of days ago we looked together at the paper and they don't state it so clearly. They just cherry pick something and it's not so clear.
Okay.
But they presented the paper like sick people get the synchronized behavior and healthy people not. And then I gave Nizam and Metal data from the internet of sick and healthy people. And okay, I don't want to.
Yeah. Okay, sorry.
Like if you're, you need to be more focused, so you're more you have more synchronization. Because you're more focused, it is harder for you.
Start thinking about doing your balance.
Ronnie, sick people, they got more synchronized?
They're supposed to be more
Because they're focusing on working to make themselves stable.
This is the theory behind that. When it's not anymore unconscious, but you need to put some cognitive
they're really
effort
focusing
on
in order not to fall.
posture, it starts to become synchronized. But it's a theory, it's not proven.
Good. So for the analysis, Ronnie gave us data from Physionet. It's a free data, I think from a real...
Yes. All over the world, people can upload.
Yes. So we first will go through the graphs, and then we will talk about the code. So first we have y-axis is the imaginary part of the Hilbert transform, and the x-axis is the real data. So we see that we have some chaos. We don't have a periodic system. Just want to show the difference.
Actually, the y-axis is the Hilbert transform, not the imaginary part. What you mean is the imaginary part of the analytic signal, but the analytic signal was composed of the real part, which is the original time series, plus I times the Hilbert transformed of the real data, but it's the Hilbert transform. So when you plot it, you have on the x-axis, as you showed, the real data, the measured data, and then on the y-axis you have the Hilbert transformed. Everybody remembers what the Hilbert transform is doing, right?
Yes, I will just show.
Okay.
So you have the blue signal of sinus in some frequency, and when we change the frequency, and the red is the Hilbert transform. So he moving the signal pi over 2, the phase pi over 2, and it is adapting to the signal. So here you can see it's remained the same, and here the signal is have different frequencies. So also the frequency of the Hilbert transform is by this signal. And if we plot the Hilbert as the function of the signal, we see some very beautiful circle. So we can see it's a periodic. It's a periodic system. This is our data. So the first graph was on this data that is very noisy. When we say left right, it is x, and back forward is y. This is for the sick subject, and this is the data from the healthy subject. Very noisy. Just remember this noise. Now we showing the phase of each
phase difference.
The phase differences, yes, and we can see that we don't see some plateau. We see that we have no synchronization. It is the graph of the sick subject, and
okay, so the red is
the back
direction, the phase, and the black is for
left right.
And the blue is then the difference between the two. Okay. But you see already the problem with the phases, right? You see this, everybody?
They are not going together.
Yeah, no, not going together, that's okay. If they are not synchronized, they should not go together. But what's the problem on the phase? If you do some work and you calculate the phase and you get such a phase plot, what would you...
I would do it between minus pi and a half to pi and a half.
No, this is cumulative.
Cumulative, yeah.
Okay, that's fine. but what is not very realistic for a physical system that has some oscillations. You would not expect to get something like this, that you have a plateau here, you know. The phase doesn't change, it's not physical. You have a oscillating system. I mean, it can go with a lower frequency, then it would only slightly increase, or it goes with a higher frequency, then it increases faster. But if it plateaus, there's something wrong with there's too much noise in the data. You cannot determine properly the phase, obviously. And we saw the data, they are very noisy.
So what do you need to filter that?
Yes.
Yes.
You need to.
So.
And also yeah.
In the article they show this. This is for. Want to show? Okay. So this is for the sick subject. You can see that his data is more clearly, and the phase differences are we can see more readable analysis, and I want you to remember what we said at the beginning, that when the eyes is open, we don't see at the beginning the synchronization. We see after 100 seconds some plateau that can present some phase synchronization. And this is also for the sick subject, but with closed eyes. This is the phase differences. Already from the beginning, we have phase synchronization. So we think that our analysis is not good because we have a lot of noise, and here we don't have noise. So. And this is our results for the healthy.
Same problem. Yes.
So we have.
So one needs to. I didn't let them do this because you need to. I don't know if you can save the data for this analysis. They are too noisy. You have to resample them, filter them, and to see if you really have oscillations you can use for the synchronization analysis. But important take-home message would be
to look if you have noise and to filter it.
To look if you have this nice circles, right? You plot. You always, before do synchronization analysis, I mean, when you did it on EEG, of course you get nice alpha oscillations. Then you don't need to check, you know. But if you get such noisy data, you always check the plot Hilbert transform versus real data, and you see if you get nice circles. If you don't get, forget about calculating a phase. It's completely unreliable. Right?
We wanted to talk about the VR center issue, but she said that it's not important anymore.
We will hear about this next week, and instead of being in the VR, we do some other experiments, but I still hope it will be interesting for you guys to see it, and you can, there are all nice people there, you can ask questions about what they do and why it's important and treatments and stuff like this. And yes, we are going to meet again at 12 o'clock at the same place where we met last time, next to the sports center. Yeah. Good.
Will the shuttle be at the entrance where it was?
No, you came to the entrance, but we met at the sports center. So
502 or?
Yes, better to meet at sports. I mean, actually, it doesn't matter. We can also pick you up at the exit, but don't be late. So either be at the sports center or Whom did you notify? You were in touch, right? No. Yes?
With him?
Yes.
Yes.
Ah, okay. Sorry. So if you cannot make it to the sports center and you come to the exit, then write me
Okay.
that you're on the way and we wait for you. We don't miss you. Good. That's it basically. Thank you very much. And yes, so let's meet next week for the trip to Shiba. תודה רבה.
תודה.
תודה רבה. שבת שלום.
שבת שלום. Thank you.
אתה יודע, מעלה את מה שעשיתי.